Here we have a basic overview of the fuel cell system. Hydrogen is delivered at the anode. Oxygen from the air is delivered into the cathode, and they react within the fuel cell to produce electric power. The products are excess oxygen and water vapor, and on the anode side, excess hydrogen. This is a basic system overview of what the hydrogen forklift would look like. A fuel tank will deliver hydrogen to the fuel cell stack, and air will deliver oxygen through a blower. The exhaust will be water vapor and excess hydrogen, and the power will go to a control unit, which controls the electric motor that will propel the forklift.
The fuel cell for the forklift consists of a 72 fuel cell stack with a power output of 15 to 18 kilowatt. The load capacity of the forklift is 3,000 kilograms with a hydrogen storage tank with a 1.7 kilogram capacity. A mass balance was performed for the inflow and outflow of the reactants in the fuel cell. Noticing that not all the hydrogen and oxygen that flows into the fuel cell is utilized, the mass balance are as follows. For the anode side, the hydrogen mass flow rate is equal to the hydrogen in minus the hydrogen out, which is the hydrogen left over from the reaction, minus the hydrogen out, which is the hydrogen reacted. On the cathode side, the oxygen mass flow rate is equal to the oxygen inputted into the cell minus the oxygen left over from the reaction minus the oxygen that was reacted.
The hydrogen usage, the total reaction 2H2 plus O2 equals 2 hydrogen, 2 oxygen, which water. We have 2 electrons for each mole of the hydrogen. Charge transferred equals 2 Faraday's constant times the amount of hydrogen. Dividing by time and rearranging, we get the hydrogen usage equals I divided by 2 Faraday's constant, which I, in this case, would equal the current. And as you can see down here, we got the values for the molar mass of the hydrogen 2 and Faraday's constant, and which gives us the hydrogen 2 usage. Typical values for the volt constant equals 0.6. The desired power is between 13.2 and 18 kilowatts for our case in this project. We got the H2 usage minimum and the H2 usage maximum here. And assuming 16 hours of daily use in a 5-day work week, we get the yearly H2 usage minimum and the usage maximum, which is 345.95 kilograms a year for the minimum and 471.74 kilograms per year for the max. And here we have the hydrogen fuel cell efficiency, which the max efficiency we can achieve is the free energy available divided by the reaction energy. which is about 83%. And we also have the efficiency according with the low heating value. And it's just the voltage divided by E, which is the thermodynamic reversible voltage. And we end up getting 0.54, 54%. And the fuel efficiency, 1 over gamma, which in gamma we're using 1.2, which will give us a 0.83 efficiency. And the efficiency of the fuel cell is all three of these efficiencies multiplied by each other, which for our case would give us a 38% efficient fuel cell.
To determine if our forklift will be usable in the forklift market, we will calculate the levelized cost of energy of our fuel cell forklift and a battery-powered forklift of similar capability. These calculations will be evaluated for the life of the forklift systems. Once we have our cost analysis, we will compare the key benefits here of each of the forklift systems in the future. And here are our references.